Hello all. In the last class we were discussing about language evaluation criteria. There we saw some points, that is like readability, writability, etc. And in addition to those factors, several other factors influence the basic design of programming languages. Okay. And the most important of these are computer architecture and programming design methodologies. So we'll look at computer architecture first. And the basic architecture of computers had a profound effect on language design. Okay, so the basic architecture of computers had an effect on language design. That is, most of the popular languages of the past 50 years have been designed around the prevalent computer architecture, and that is known as von Neumann architecture. Okay, after one of its originators, John von Neumann. Okay, so these languages are called imperative languages. In a von Neumann computer, both data and programs stored in the same memory. So both data and programs are stored in the same memory. The central processing unit, that is a CPU, which executes instructions, and that is separate from the memory. Okay, so we have a CPU and that is different from the memory. Therefore, instructions and data must be transmitted or piped from memory to the CPU. So memory is here, and instructions and data will be stored there, and that will be transmitted to CPU. Results of operations in the CPU must be moved back to memory. So what happens when the CPU performs some computation, the result should be stored somewhere. So this result of different operations should be moved back to the memory. And nearly all digital computers built since 1940s have been based on the von Neumann architecture. So most of the computers that are designed uh, are based on actually this von Neumann architecture. And because of the von Neumann architecture, the central features of imperative languages are variables which model the memory cells, assignment statements which are based on the piping operation, and the iterative form of repetition, which is the most efficient way to implement repetition on this architecture. Okay, so we have a von Neumann architecture, and based on that we have imperative languages, and the central features of imperative languages means their variables which model the memory cells. Okay, variables means they represent the memory cells, and we have assignment statements. That is again a central feature of these imperative languages, and these are based on the piping operation. Okay, assignment statements, and the iterative form of repetition. Okay, which is the most efficient way to implement repetition on this architecture. So we have iterative form of repetition. So operands in expressions are piped from memory to the CPU. So that is why we have this piping operation. So we have operands in expressions, and they are piped from memory to the CPU. And the result of evaluating the expression is piped back to the memory cell represented by the left side of the assignment. Okay, so in an assignment statement we have both left hand side and right hand side, and right hand side values will be copied to or stored in the left hand side. Okay, so the result of evaluating the expression is piped back to memory cell, and that is represented by the left hand side of the assignment. And iterations is fast on von Neumann computers, because instructions are stored in adjacent cells of memory, and repeating the execution of a section of code requires only a branch instruction. Okay, so we have iterations can be implemented here, and that is on this von Neumann computers. These are very fast because instructions are stored in adjacent memory cells instructions are stored in adjacent memory cells of memory and repeating the execution of a section of code. Okay, suppose we need to repeat execution of a section of code that requires only a branch instruction. We just need to branch to that particular location. Okay, and this efficiency discourages the use of recursion for repetition, although recursion is sometimes more natural. Okay, so what we do here is we most of the time um, we will not use recursion here, because this iteration is actually more fast. Okay, because uh, we have these instructions and they are stored in adjacent cells of memory. So repeating this instruction means we just need to branch to that particular location. Okay, and execution of a machine code program on a von Neumann architecture computer occurs in a process called fetch execution cycle. Okay, so how we can execute machine code on this architecture, and that is based on, or that process is known as fetch execute cycle. And we know these programs reside in memory but are executed in the CPU. So at the time of execution, these instructions or data must be brought to CPU. Okay, so each instruction to be executed must be moved from memory to the processor, and the address of the next instruction to be executed, and that is maintained in a register, and that is known as program counter. And fetch execute cycle can be simply described by our code, and that is this code. So we have fetch execute cycle, and the fetch execute cycle can be simply described by this step. That is, we have initialize the program counter and repeat forever. Okay, so fetch instruction pointed to by the program counter. So program counter contains address of the next instruction to be executed. So we'll fetch from there and increment the program counter to point at the next instruction. So after fetching instruction that is pointed to by the program counter, the value of this program counter should be incremented to point to the next instruction. Okay, and decode the instruction. So once we fetched the instruction, what we need to do is we just decode the instruction to get what is meant by that instruction. Okay, so that is we need to get what is the operation of that particular operation given in that particular instruction, and what are the operands of that instruction, whether the operands must be brought to uh, registers or memory, whether the operands reside in memory, or whether the operands are supplied as part of this instruction, etc. Because sometimes we have constant operands. Okay, and we need to decode this instruction. Decoding is just understanding the instruction. Okay, and then based on and the relevant operands must be brought to this memory, and after performing all this, execute the instruction. Okay, and enter repeat. So this will be repeated forever. So we have the program counter that points to the next instruction to be executed, and then we have increment the program counter. So fetch the instruction, then increment the program counter, then decode the instruction. So decode the instruction means that is instruction is examined to determine what action it specifies. Program execution terminates when a stop instruction is encountered. On an actual computer, a stop instruction is but rarely executed. Control transfers from the operating system to a user program for its execution, and then back to the operating system when the user program execution is complete. Okay, so what happens is we do not have, or we do not execute this stop instruction usually. What we do on actual computers is that we have control on this instruction that is being executed. So after that, control transfers from the operating system to a user program for its execution. So usually the control will be in operating system. So then we'll start reading from the user program. So that's why the control transfers from the operating system to a user program for its execution. Okay, and then back to the operating system when the user program execution is complete. So the when user program execution is complete, what happens is that the control is given back to the operating system. Okay. So in a computer system in which more than one user program may be in memory at a given time, and this process is far more complex. Okay, so uh, when we have more than one user program in memory at a given time, so everything becomes very complex. And we can just have a look at a functional or applicative language is one in which the primary means of computation is applying functions to given parameters. Programming can be done in functional language without the kind of variables that are used in imperative languages, without assignment statements and without iteration. Okay, that is the um, features of this functional or applicative program. So many computer scientists have expounded on the benefits of functional languages. As I discussed earlier, we have scheme language. It is unlikely that they will displace the imperative languages until a von Neumann computer is designed that allows efficient execution of programs in functional languages. And among these, um, the most important one is or John Backus and the principal desire of the original version of Fortran. And in spite of the fact that the structure of imperative programming languages is modeled on a machine architecture, rather than on the abilities and inclinations of the users of programming languages, some believe that using imperative languages is somehow more natural than using a functional language. So what we said earlier was we have functional languages, and when we use these functional languages, we do not need the kind of variables that are used in imperative languages and the kind of assignment statements, and even without iteration. Okay, so that is the benefits of this functional languages. And in most of the case, some functional languages um, displays the imperative languages until a von Neumann computer is designed. Okay, and we have um, in spite the fact that the structure of imperative programming languages is modeled on a machine architecture, abilities and inclinations of the users of programming languages, some believe that using imperative language is somehow more natural than using a functional language. Okay, so if you use imperative language, even though with all these benefits are there, using these imperative languages is more beneficial or um, more natural. So these kind of people believe that even if functional programs were as efficient as imperative programs, the use of imperative programming languages would still dominate. Okay, so even though we have popular functional languages, we have um, this imperative languages are still uh, popular. And the next criteria is programming design methodologies, and we discussed about different types of programming. The late 1960s and early 1970s brought an intense analysis of both the software development process and programming language design. Okay, so we have software development process and programming language design. So an important reason for this research was the shift in the major cost of computing from hardware to software as hardware costs decreased and programmer costs increased. And we have an intense analysis on both software development process and programming language design. And an important reason for this research was the major cost of computing from hardware to software. And we know as we have this hardware cost that got decreased, but the programmer cost increased. Increases in programmer productivity were relatively small. Even though programming cost is increased, increase in programmer productivity is not that much high. So in addition, progressively larger and more complex problems were being solved by computers. Progressively large and more complex programs were being solved by computers. Rather than simply solving sets of equations to simulate satellite tracks, as in the early 1960s, programs were being written for large and complex tasks, such as controlling large petroleum refining facilities and providing worldwide airline reservation systems. So, in this in the early 1960s, um, actually the computers were simply solving sets of equations to simulate satellite tracks. Okay, now programs were being written for large and complex tasks. Okay, such as controlling large petroleum refining facilities and providing worldwide airline reservation. We are using computers, or we are writing programs for all these purposes. And the new software development methodologies that emerged as a result of the research in 1970s were called top-down design and stepwise refinement. Okay, and the primary programming language deficiencies that were discovered were incompleteness of type checking and inadequacy of control statements. That is because of the requirement of extensive use of go-tos. So we have, as part of 1970s research, we have a top-down design, that is a software development methodology, and stepwise refinement. Okay, and the primary programming language deficiencies. So when we have all these things, the primary programming language deficiency were completeness of incompleteness of type checking. So type checking is some kind of checks that is used to identify types of or data types of different programming language constructs or variables. Okay, and inadequacy of control statements. What made this control statements very inadequate is that we need extensive use of quotas. So most of the places we use quotas, that made it very um, less efficient control statements. So in the late 1970s, a shift from this procedure oriented to data oriented program design methodologies began. So we have data oriented methods, emphasis data design, focusing on the use of abstract data types to solve problems. So we have a shift from procedure oriented to data oriented. So in data oriented, what happens, the more emphasis is on data design. Okay, focusing on the use of abstract data types to solve these problems. And when we talk about this data design, we have data abstraction to be used effectively in software design. Okay, so it must be supported by the languages used for implementation. So we need to implement this data abstraction. The first language to provide even limited support for data abstraction was Simula 67. Okay, Simula 67, that was in 1973. Although this language certainly was not propelled to popularity because of it. Okay, the benefits of data abstraction were not widely recognized until the early 1970s. However, most languages designed since the late 1970s support data abstraction. Okay, we'll be focusing on data abstraction later. But the first language that gave support for data abstraction was Simula 67. But because of this data abstraction, the Simula was not that much popular. Okay, even though it had this data abstraction capabilities. And after this, in late 1970s, most of the languages give support for data abstraction. And the latest step in the evolution of data-oriented software development, which began in the early 1980s, is object-oriented design. Okay, so object-oriented methodology. So we were discussing about the data-oriented, and based on the data-oriented development, so we have this object-oriented development. And object-oriented methodology begins with the data abstraction, which encapsulates processing with data objects and controls access to data and adds inheritance and dynamic method binding. Okay, so these are the features of this object-oriented design. And inheritance is a powerful concept that greatly enhances the potential reuse of existing software. Okay, so we have this inheritance is there. Inheritance actually gives us the power to reuse existing software and thereby providing the possibility of significant increase in software development productivity. Okay, and this is an important factor in the increase in popularity of object. So that's made this object-oriented design very popular. Then dynamic method binding allows more flexible use of inheritance. So we have this method binding that is done during runtime. Okay, and object-oriented programming developed along with a language that supported its concepts. So we have language like Smalltalk. And although this small talk never became as widely used as many other languages, support for object-oriented programming is now part of most popular imperative languages, including ADA 95, Java, C++, and C Sharp. And object-oriented concepts have also found their way into functional programming, okay, as well as logic programming. Okay, so even though we have this object oriented programming language separately, most of these features are available in functional languages or logic programming. Okay, in all these languages, all these concepts you can see, and procedure oriented programming is also there, and that is in a sense the opposite of data oriented programming. Okay, that is, although data-oriented methods now dominate software development, procedure-oriented methods have not been abandoned. Okay, so as we know, this data-oriented methods now in most of the software development applications we use data-oriented programming languages, but procedure-oriented methods have also an impact, or that is widely used in most of the places. On the contrary, in recent years, a good deal of research has occurred in procedure-oriented programming, okay, especially in the area of concurrency. So we have a lot of research happening in procedure-oriented programming as well, especially in the area of concurrency. So concurrency means we have more than one programs executing simultaneously. So these research efforts brought with them the need for language facilities for creating and controlling concurrent program units. Okay, so we have different research going on with concurrency. So these languages should support concurrent program units. ADA, Java, and C Sharp include such capabilities. Okay, so these are the main programming design methodologies. And thank you.